Welcome to our deep dive into derivatives. You sent over some of Professor Wu's materials, and wow, he seems like a really good teacher.
Yeah,
And it's clear that derivatives are a huge part of getting into machine learning.
absolutely.
And actually something like 99% of machine learning algorithms use them.
Yeah, it's incredible.
So let's dive into why they are so important.
Yeah, you know what I think is really cool about derivatives is they give us this ability to see how little changes can really affect a whole system. Like it's not just inputs and outputs, it's like understanding those connections between the two.
I see what you mean. But when I hear derivative, I kind of freeze up.
Yeah.
What exactly is a derivative?
Yeah. So think of it like a blood test, right? So the input is like all the different things they test in your blood, and then the output is something like your probability of getting cancer.
Okay.
A derivative tells you how sensitive that output is to each of the inputs. So like if one of the things they're testing in your blood changes just a little bit, the derivative tells you how much that changes your overall risk.
So it's not just like a yes or no. It's telling you like the degree to which they're connected.
Exactly. And it really helps us understand which inputs matter most and how we can kind of steer the system towards an outcome we want.
So that's why machine learning uses them so much.
Absolutely.
But how do we actually find these derivatives?
Okay, so there are 7 essential rules that we can use to find derivatives, and they might seem a little abstract at first, but I promise they're all really powerful tools.
Lay it on me. What's the first one?
Okay, let's start with an easy one, the constant rule. And this one basically says if something is not changing, then its rate of change is 0. It's like picturing a flat line on a graph. It's not going up or down, so its derivative is always going to be 0.
That makes sense. If something's constant, its derivative is 0. What about when things are changing?
All right, well, that's where the power rule comes in, and this is all about exponents. So let's say we have 3x cubed. The power rule says to bring that 3 down, multiply it by the coefficient, and then decrease the power by 1.
Okay.
So the derivative will be 9x squared.
All right, so I'm starting to see a pattern here. What about when we want to find the derivative of a bunch of terms added together?
Oh, you're talking about the sum rule. This is a really simple one where you just find the derivative of each part separately, and then you just add all the results together.
Okay, that one seems easy. What about when we need to find the derivative of functions that are being multiplied together?
That's when we would use the product rule. So for example, if you have something like 2x plus 2 times 2x squared, you can multiply all that out. But the product rule gives us this nice little formula to find the derivative directly.
Nice. So it makes things faster.
Exactly.
Okay, but math can get really complicated quickly.
Yeah.
What about when we have special functions like exponentials?
Yeah, so exponential functions use that special number e, which is about 2.718. And they have this really interesting property where the derivative of e to the x is just itself.
Wait a minute, so it stays the same even after we take the derivative. How does that even work?
Yeah, it's pretty wild, right? He has some special properties that make it super important in calculus and tons of other fields, too.
Wow, my mind is blown. Okay, what about logarithmic functions? So those have always been a bit of a mystery to me.
Yeah, logarithms can be a little tricky, but think of it like this. They basically tell you what power you need to raise a base to get a certain number. So we often use base 2 or base e, which gives us the natural log, or ln. And there are rules for finding the derivatives of both natural logs and logs with other bases. We can use what we know about those other rules and just convert things into a form that we can work with.
Oh, so it all ties together. I'm starting to feel like I can actually use these rules.
Right.
What about that last one, the chain rule?
The chain rule is where things get really fun. This is for when you have a function inside of another function, kind of like those Russian nesting dolls. And the chain rule helps us unpack these layers, find the derivative of each one, and then multiply all those results together.
That sounds complicated.
Yeah, it can be, but it's super powerful for those more complex functions.
Well, this is all starting to make a lot more sense. But you know what I'm wondering? If we're actually using these derivatives, how do we know we got the right answer? It's not like there's an answer key out there.
That's a really great point. Verification is super important, especially when things get really complicated. The cool thing is we can actually use programming to help us out. So we can use Python and a library called Autograd to automatically find the derivative and check our work.
Oh, wow. So it's like a safety net. We can double check that we're on the right track.
Exactly.
Okay. Well, before we get too far ahead, I know there's a whole other concept we haven't even talked about yet. Integrals.
Yes. Integrals are kind of like the opposite of derivatives. So derivatives tell us about how things are changing at one specific moment, but integrals are all about finding the total effect over a whole range.
Okay, I'm listening. Can you walk me through that a bit more? Like, what exactly are integrals, and why do we care about them?
Okay, so imagine a simple linear function that creates a triangle on a graph. Finding the integral is basically like calculating the area of that triangle. It's about understanding the bigger picture, not just what's happening at one point.
So if derivatives are about slopes, then integrals are about areas.
You got it. And we can find integrals by integrating, which is like finding the antiderivative.
This is all so interesting. It feels like we're learning a whole new language for how to understand how things change.
That's exactly what calculus is. It gives us these powerful tools to analyze and change systems in all sorts of fields, from physics and engineering to finance and, of course, machine learning.
Wow, I'm really starting to understand how important this is, especially for my machine learning journey. But before we move on, let's take a second to absorb all this amazing information. We've covered a ton, and I want to make sure you're feeling good about everything before we move on.
Yeah, that sounds good. It is a lot to think about, but, you don't have to be a calculus expert to see how powerful this stuff is, especially in machine learning.
Yes.
Exactly. I'm trying to get the big picture, How do we use these, abstract ideas to solve real problems?
Okay, well, let's think back to the blood test analogy.
Okay.
Remember how derivatives can help us figure out which drug to take to lower our risk of cancer?
Yeah, that was super interesting. I want to know more about that.
Okay, so let's say the derivative of the function for one of the blood markers is a tiny positive number, like 0.001.
Okay.
That tells us that even if we increase that marker by a lot, the probability of cancer only goes up a tiny bit.
So even if a drug targeted that marker, it wouldn't really be that effective.
Exactly. But now imagine another blood marker has a derivative of like -6.
Okay.
So that's a much bigger number, and it's negative.
So that means that if that marker increases, the probability of cancer actually goes down, and by a lot.
You got it. And just to make it even clearer, let's say there's a third marker and it has a derivative of +20.
Oh, wow.
Yeah.
So even a little increase in that one could really increase the risk. Exactly. And we'd want to avoid anything that would increase that marker.
For sure.
This is why understanding derivatives is so important for making decisions. It's not enough to just know the inputs and the outputs we need to know how they're connected, how those changes flow through the system.
It's like we suddenly have a flashlight in a dark room and we can finally see what's going on.
Yeah, that's a great analogy. And that's exactly what derivatives do in machine learning. They let us see those connections in the data so we can change the inputs in a way that gets us the results we want.
So even if I'm not calculating derivatives every day, just knowing about them helps me understand how these machine learning algorithms work.
Absolutely. And Professor Wu mentioned that machine learning isn't all about calculus.
Right.
It uses probability and statistics, linear algebra. It's this whole big world of knowledge.
It's crazy how all these different fields come together to make machine learning.
It's really cool. And since you understand derivatives, now you're in a great spot to really see what machine learning can do.
Yeah, this deep dive is really making me think. Before we wrap up, I'm curious if there are any other examples of these derivative rules at work in the real world. I mean, we talked about medicine, but are there any other areas where they're super important?
Oh, yeah, tons. In finance, they use derivatives to analyze market trends and manage risk.
Okay.
Or in physics, they're essential for understanding things like motion and forces and energy.
Huh?
Even video games use derivatives to make the movements look realistic.
It's crazy how something that seems so abstract can be used in so many different places.
I know, right? That's what's so cool about math. It gives us this way to understand how the world works. And derivatives in particular, they let us predict and control how things change.
Like we have this secret code to figure out the universe.
I love that. And as you learn more about machine learning, you'll see how this secret code is used to create algorithms that can learn from data and make predictions and even solve problems that are really hard for humans to figure out.
This deep dive has really opened my eyes to all sorts of possibilities. It's amazing how much I've learned about derivatives.
And this is just the beginning. There's so much more to learn about calculus and what we can do with it. But the important thing is you have a good foundation to build on now.
Yeah, I feel ready to keep learning and exploring. I think this is going to be super helpful for my machine learning journey.
I think so too. And you have those great materials from Professor Wu to help you out.
Right.
Plus, there's tons of stuff online like courses and tutorials and even whole communities of people who love calculus and machine learning.
Awesome. That's great to know. And I bet our listeners are already on their way to mastering all this. But before we go, I want to leave them with one last thought.
Okay, what is it?
So if derivatives are all about how things change, and machine learning is about creating algorithms that can learn and adapt, what does that mean for the future? What can we do when we put those two ideas together?
That's a great question, and it's one that I think we'll be trying to figure out for a long time. But I think being able to understand and use the power of change is going to be more and more important in a world that's always changing.
That's for sure. Well, thanks for joining us on this deep dive into derivatives. We covered a lot, but I hope you've learned something new about how cool and powerful calculus is and how it's shaping the future of machine learning and even beyond. Keep learning and exploring, and you never know what amazing things you'll find.
Yeah, have fun with it.